I've been asked by some customers to go over a typical procedure that I use when I'm using the CNC machine. And these customers are generally beginner customers, so I'm going to keep a lot of complexity out of it. I'm just going to be keep it as simple as possible and not have to worry about too many variables. So generally on a CNC router, there's going to be a specific point of origin, and I generally have this as the origin, my bottom left, or on a flat table, it would be the one closest to me and probably to the left. And I do this because it's the way I look at things on the screen of my computer, and it's for one thing, it makes it so it's safe for me, so I can. The machine is going to move in the way I would expect it to move. So I can pretty much make my origin anywhere on the table I want, but and that's going to be done more of a manual as a manual operation. So first, I'm going to put the machine at its home position. It's going to engage the limit switch once, and then it's going to go slower and engage it again, just so it makes a more accurate position. So you do that to the x-axis. Okay, now that the machine is located at what I would consider the origin, or 0, 0 for the machine, I'm going to go ahead and zero out the DRO. So I'm going to zero the X, zero the Y. I haven't touched the Z axis yet, but just because I've zeroed it there doesn't mean that's where I want to have the origin for the workpiece. So I'm going to find around a 12 by 12 piece here somewhere and use that as a material to mill, because what I'm doing on the machine right now is about those dimensions. So let's see, maybe this one will work. This is 11 or 11 and a half by 14. This one will work, so I'm just going to go ahead and use this piece. And then the next operation I'm going to show is how I go from Autodesk Inventor to Kambam, and then we'll come back to the machine and mill it out. This video is intended as a beginner's introduction to quickly show a general process from CAD software to creating machining operations with CAM and finally cutting out the parts. The CAD software I'm using is Autodesk Inventor. After I create all the parts in CAD, I lay out the parts flat so I can convert them into a drawing. The flat layout will allow me to create a simple two-dimensional drawing of all the parts that will then be saved in a format that my CAM program can open. The title block and border is removed, as this is not necessary in the CAM process. At this point, I'm not worried about placement of the parts. I like to do this in the CAM program since it's easier for me to move and rotate the parts. I save this file as a DXF file or drawing exchange file. This is a file format that can be opened by most CAM programs. I'm clicking on the Save Copy As under the File menu to be able to save as a DXF file. For this demonstration, I'm using Kambam to create the machining operations that will be applied to the geometry in the DXF file. The light gray grid that is shown above and to the right of the red and green lines is the 4-foot by 8-foot boundary of the machine, and the lower left corner where the red and green lines intersect is the origin, or 0x and 0y location. To the right is positive x, and going up is positive y. Once I open the DXF file, the parts will be laid out as they were shown in the drawing view of Autodesk Inventor. None of the lines and arcs that form the outlines of the parts are joined, so joining them is the first thing I do, which is simple. Select all of the parts and use the join feature. I am separating the parts so they can be individually moved and rotated. This could have been done in Autodesk Inventor more easily, but it's still pretty easy to do here. Before I move the parts to their final locations, I will do all of the machining operations, like drills and profiles. Drills are machining operations that can create holes equal to or larger than the diameter of the end mill. The way a drill operation with a small end mill can make a larger hole is by a spiral movement that removes a large area of material. This will be more evident when the toolpath is generated later. Profiles are sideways milling operation that will cut along the inside or the outside of the geometry. I'm doing the machining operations now so I will know how close to move the parts to each other. The first operation I'm doing is the drill operation. I select all of the circles, excluding the circles that will serve as counterbores. I then apply 2 drilling operations on these circles, one for roughing and one as a final finishing pass. Oddly, my screen recording program didn't pick up the selection rubber band, so it looks like I'm just eyeing it. Before I go any further, I need to set the thickness of the material that I'll be cutting. This is called the stock. The thickness of the material is 3/4 of an inch, but I set the stock thickness to 0.81 inches so I can make sure all of the parts are cut all the way through. This is really only important if you're cutting out a lot of area and the material is not perfectly flat. I do this for all of my milling anyway, to keep things simple. Now I'm selecting all the circles that will serve as counterbores, which will only be milled a little less than 3/8 depth. Each time you see green geometry appear, I'm pressing Ctrl T to display the toolpaths. This gives me a good indicator to what geometry I still need to apply machining operations. You can see here that I select the 2 drill operations that belong to the counterbores, and I change the target depth to -0.35. The next machining operation is to cut along the outlines of the parts. This operation is the profile operation. Now that all of the machining operations have been applied to the geometry, I will set the first of each operation as roughing. I use a style for this which changes some of the parameters, like the roughing clearance dimension and the depth per pass. After pressing Ctrl T to see the toolpaths, I can start moving the parts into position. The green geometry represents curved movements, and the blue geometry represents straight movements. The green and blue lines show the center line of the toolpath. So if the 2 center lines nearly touch, the end mill will move inside the neighboring operation. I find this to be one of the more important aspects of part location, as the end mill will need to be passing through less fresh material, which will lengthen the life of the tool. End mills are not cheap, so I spend the time to do this on every job. When a part is moved, the toolpath geometry is left behind, so I press Ctrl T often to generate toolpaths. Once all of the parts are moved into locations that are satisfactory and will be within the boundaries of the material I have in the shop that will be used for the job, I can start adjusting the holding tabs. Holding tabs are small portions of material that the CNC router will avoid so that the parts will be held in place. I try to position holding tabs where there is a material between and around parts rather than positioning them between parts. This is a practice I follow, so I make sure any sections of material that can come loose will not. There are small areas that will not fit holding tabs, but those are typically small enough not to get jammed into the machine and will just be sucked up in the vacuum anyway. Kambam gives you the freedom to define the geometry of the holding tabs. Holding tabs can be set as square or triangular. The square tabs cause the movement of the cutter to stop and move up, then across, and then down. Triangular tabs allow the motion to move up, across, and down more gradually, and can allow the machine to work in a constant velocity. You can also define the height and width of the tab. I set the height about half of the thickness of the material, so I will have an edge that I can use a bearing on a router bit to trim off the holding tabs later. You'll notice that I'm moving 2 holding tabs where you would expect only 1. This is because the profiles have 2 machining operations, a roughing operation and a finishing operation. Each operation has the same tab locations. Now that all the holding tabs have been positioned, I want to inspect the overall toolpaths. I use the Alt key to rotate the drawing area so I can see the depths of the counterbores to confirm that I did not forget to do those. I am saving the file as a Kambam file, and then I save a toolpath file which contains the G-code. G-code is a set of instructions that the machine's control program will understand. This G-code file will have either a .nc or a .tap file extension. If you're watching this video, then this may be your first time creating a G-code file. Make sure you have the correct post processor in the configuration. A post processor takes care of any small inconsistencies between G-code for different control programs. For example, the G-code that will work with Mach 3 may not completely work with, say, Linux CNC. If this is not done, the control program may give you an error or unexpected geometry, which unexpected geometry will cause unexpected movements, and that is not good on a moving machine with a spinning cutting tool. So my camming is done. I can go ahead and load the file. And this looks like it's the file here. Open it. And you can see that after I did my X0 and Y0, all of the parts are in the positive region. If I move the machine, you'll see the machine move in the X-axis direction. You'll also see that this line moved. So I'm going to go back and go forward. Okay. I don't want this to be my origin because what I did is I put my material here. So I want this to be my origin. And all I'm going to do is I'm going to move that ML just above the screw here. So we can also confirm that we're within our bounds using Mach 3. Okay, so I'm going to move this to this corner here. Okay, so I've moved the end mill in that location. See the end mill here. So it's just above the screw. I haven't zeroed out the DRO yet. DRO means digital readout. And I also need to go down with the Z-axis, but I want to zero out my X and Y first because I want to see if I'm within the bounds, just for confirmation. All right, so I'm going to move the X all the way to the end. Okay, that should be it right there. And it looks like I'm off the... Oh no, I'm still there. So I still have a little bit of material. So I'm good on the X. And I know I'm going to be good on the Y, but I'm going to test it anyway, just to make sure. Switch this to the Y. All right, so I'm going to move this up. There's nothing around on this corner here, but over here, let's go ahead and go above that. And I'm still good on the Y-axis there, so I should be fine. So I know that my area is good using this as an origin, and my workpiece is good. So now I'm going to go around the center of the workpiece and zero my Z. If you have a pretty flat surface, then you shouldn't have. It doesn't really matter where you zero the Z. But if your surface isn't that flat, maybe the workpiece is warped a little bit. You'll have that happen on very large pieces. You might want to maybe going to the lowest point or going to the sort of the center of that workpiece. Okay, so I'm gonna put it to step, and I'm going to lower it incrementally. All right, as I'm lowering it, I am spinning it at the same time. So as I go down one, I'll spin it, and when it stops to spin, I know I'm at the surface, so I'm going to zero that out. Okay, so I'm going to zero the Z-axis because it's on the surface. And now I'm going to pull the Z-axis up, so just in case it does any sideways motion, I don't have to worry about the end mill getting damaged. Okay, so now I can go ahead and start the milling process. So that is, I'm going to turn on my vacuum first. I use the flood for my vacuum, and then I'm just going to press cycle start. Since I know that is the location, I'm pretty confident that everything is set correctly, and I've tested my bounds. And I also know that my VFD is on, so when I press cycle start, everything should start. The spindle is spinning, and I can see my frequency here on the VFD, so I know it's working. Now that it's finished doing the routing, I'm going to move the gantry out of the way. And you'll see where the machine left holding tabs. There's one here, here, here. All the places that you saw the holding tabs being placed in the CAM program. So I'm going to go ahead and cut these parts out and show you the next process. And I use a multi-tool to cut these parts out. You can use a hammer and a chisel, but you may get some blowout on the back if you do that. One thought is you can take this part off and take the holding tabs off from the back end, but I find this is a little bit better because it's more stable. If I have a hard time getting some of these holding tabs out, I will use another tool and take this entire thing off first, because there are some circles or curves that may be a little bit too tight, or certain areas like this one was right around here was pretty tight. This one was pretty tight. If I had a holding tab inside here, that would have been almost impossible to do with this size of a blade. I would have to get a smaller blade, or do it from the other side. Maybe use another tool to get that out. The holding tabs will leave you with these triangular or square, depending on the configuration of your holding tabs. You'll be left with this stock on the edges, and what I do is, you can see the height of the tab, and then you can see that there's a nice smooth section just above the tab, so I can take that and use that as a bearing guide. So let me show you my method of getting rid of these tabs quite quickly and easily. When I route these edges, I'm using a bearing with the standard router bit. So the bearing is going to guide along the bottom edges. There's also router bits that have the bearing on the top, and you just spin this part over and the bearing will be riding on the top of the part. So if it's like this, you'd be doing it like this, where the tab is on the bottom. But in this case, the bearing is on the bottom, so the tab is going to be on the top. You'll see that there are some smaller pieces here that I'm going to have to use some kind of device to hold this piece while I'm routing it, because I don't want my hands to get anywhere near this router bit. You'll notice I went around, I didn't go right on top of the tab. I went behind the tab, and I'm only going in one direction. This is the conventional direction. This is not the climbing direction. So I'm going against the spinning of the blades. I do this because whenever I will get anywhere close to the tab, this part tends to want to push out at me. So if I go to already a smooth section, I have a less occurrence of that. So you can see that was done pretty quickly. I could have done it a lot quicker, but you have to make sure that you have safety in mind when you have an exposed router bit like this.